And now let me tell you a few short words about the speaker. So our next speaker is Matteo Rosati. He did his PhD with Vittorio Giovannetti, and he then joined the group of Andreas Winter when he was still in Barcelona with a Marie Curie fellowship. And then he got also the Einstein fellowship and moved to the group of Andrea Papa for a short visit before joining the University of Roma III as a lecturer. And today he's going to tell us about secure and distributed information processing over quantum networks.
Well, thank you so much for the invitation. It's nice to come back at EACN and seeing it keeps going every year. So I'm just realized the resolution will be really, really bad on the slides because I sent them by email and was some compressing issues. So if you are not able to read something, just come back and we can write on the blackboard later. So I'm going to present a couple of works. First one I did in collaboration with the photonics group of Marco Barbieri in Rome. They did the experiment. And I think it's the very first experiment on the topic of the paper. And the second one is a collaboration with Berlin, with Anna Pappa and Ziad Shawi. So, the quantum internet, I guess this is the right venue to try to talk about it. And this slide is basically just to say that I believe we should frame it as something that opens the door to quantum advantages or the search for quantum advantages in a broad sense. So quantum technology is not just the quantum computer, right? And the moment you can basically connect quantum computers at distant locations or small quantum processors or labs that have some quantum capabilities and you make it possible to exchange quantum information at a distance, you can basically think of a broader set of technologies. Okay, so we know that of course you can do secure communication, you can do QKD in a certain sense, but you can also think of doing distributed calculations if you have computers. And of course, you can also think of improving sensing, okay? Because we also know that there are advantages in using quantum sensors. Particularly, you can increase precision in certain settings. So I'm going to present a couple of very simple protocols, actually, that you can think of use to test these ideas in the near-term picture, where you have, let's say, a central hub that is somehow capable of producing quantum stuff, quantum states, and then peripheral endpoints in the network with limited or even very limited quantum capabilities. Okay, that will use the central hub essentially as a server to provide quantum states. Okay, that's the first paper. So the idea we have Alice that prepares quantum states, Bob that receives them, and Bob cannot do very much to these states, but he has some information that he wants to estimate. For example, imagine we are trying to use quantum sensors to estimate with improved precision medical data, for example. Take a picture of the eye. I don't know about this. And of course, they have some requirements. Okay, so the first one is that Bob is asking for quantum probes because he wants to improve the precision of his sensing setup. The second thing is that they want to keep this data private, private to somebody who's controlling possibly the channel where they transmit states. And then they also want something new, let's say, with respect to standard QKD or metrology. Essentially, they want that the estimation of the quantity here is close to the true value, not because of noise that there might be here, but because of somebody who might be tampering intentionally with the probes that are sent. So this problem, people started studying it somewhat like 5 years ago or a bit more. There has been some work around here. Mostly if not fully theoretical, and people first proposed a protocol essentially based on BB84 that however had some problems. So these were people in Italy, the Maccone group, and then there was something of a follow-up by Demian Markham and Elan Kashefi, which however used the Bob that has to do some complex encoding using long Clifford sequences of gates, which however defeats a bit the purpose. Let's say you don't want to have a complex setup here, otherwise you could prepare the probes yourself. Okay. There's also been some work outside of Europe, especially in the East. I'm sorry we were not able to see the references here. So we have a nice table in the paper where we sum up a bit of the protocols that have been proposed so far in the single user setting, let's say, because then there is also families of protocols where you have a lot of users that somehow want to keep their local data private. And okay, so the main issues that we wanted to tackle with our paper are this column of attacks and this one of faithfulness. In particular, previous works addressed only the possibility of doing individual attacks. So we go full QKD in this direction. So we have a security against the general coherent attacks, which is basically the most paranoid way you could think of Eve. And she has a quantum memory. She can keep data, quantum data, and then do a big measurement to extract information. And then we have this faithfulness, which is essentially connected with an experimental requirement. So previous protocols had like something that you check, and if you don't like what you see, you abort the protocol. But this was a very hard mechanism, whereas we introduce a threshold, because in real life, maybe there is not Eve, but you would see some noise, and if the noise makes you fail the protocol immediately, then you cannot go on, okay? So this was to make it more practical. We have a threshold, you have essentially, you check this threshold. If it's, you check a certain quantity, if it's larger than a threshold, you go on and you can quantify how good you're doing. Otherwise, you say, no way, I will stop. And then we also have two families of protocols, the one-way ones, where Bob can do some measurements locally, but he cannot produce quantum states with entanglement over several parties. He will receive them from Alice. And then the completely passive Bob, in which case you use a two-way scheme. So Bob not only receives the quantum states, but he also has to send them back. The only thing he can do is basically alternate, decide whether he wants to encode the quantity they want to measure or not. The quantity we want to measure, of course, we take a prototypical example of phase estimation, okay? So let me say immediately that in the two-way picture, if you allow Bob to do very, very limited things, you cannot guarantee security against Eve, because Eve can simply try to replace Alice, okay? She will basically reroute Alice's quantum states, and she will play Alice with Bob. She will send a probe and take it and measure. And yes, they could try to check the statistics like people doing QKD, but they will notice that there was a spy only afterwards, after the information has leaked already. Okay, so let me stress for a second the two important requirements we have. Security is what you expect. So Alice and Bob don't want the estimated phase to leak to Eve. So Eve will try to do a leakage attack to extract information about the estimation procedure. And then we want faithfulness. So Alice and Bob asked that the estimated phase is close to the true value. So in this case, Eve's attack, we call it tampering, because she's trying to disrupt the estimation procedure by modifying the transmitted state. So she doesn't really want to steal the information, but she wants to make it hard for them to estimate. She wants them to make a mistake, okay? This is an example of a protocol that is entanglement-based. We also have protocols based on mutually unbiased basis. They're essentially equivalent up to some parameters. And so in this case, Alice produces an entangled state of a qubit she keeps in her lab and a certain number of qubits that she would send to Bob. The higher the number of qubits she sends to Bob, the higher the quantum enhancement, let's say, in the estimation procedure. And these qubits essentially, this is a bold 0 and a bold 1 to say they are GH-stat-like states, okay? So they're a superposition of a lot of zeros and a lot of plus states and a lot of minus states that gives you a quantum advantage in estimating the phase. She then sends Bob's part of the state to Bob, and Bob alternates at random 3 actions. One is to discard. He has these discard rounds because he wants to be protected against collective attacks from Eve. If you remove these, you don't have security against collective attacks. He can then have some check rounds where he will measure, but he will not encode the phase, okay? And then he can have the estimation rounds where he encodes the phase and he measures. They both measure Pauli-like observables, okay? And then from the check rounds, they can reconstruct essentially the fidelity of the true state, okay, to the ideal state. So this allows them to check for noise in the channel, okay? And this is what they use to perform a check and decide whether to proceed in the estimation or not. So if this fidelity is larger than a given threshold that they decided before, then essentially they decide that they estimate that Eve's presence is small, okay? Is not going to disrupt too much the protocol, and then they proceed with the estimation. It's a standard estimation procedure. So we have a theorem that tells you, based on this epsilon that you put as a threshold in your experiment, how far the estimation, the estimated value and the variance, the error, how far these quantities are from the ideal values that you would have in the absence of noise, in the absence of Eve. Okay? So somehow you're able to quantify Eve's presence, and then with that quantity, with that epsilon, you're able to bound how close the estimation is to the ideal conditions. Okay? And this allows you, depending on how far you accept to be from the true quantities, this gives you a practical way to determine the threshold, the security. The proof of this, this is a bit technical, but essentially the main problem is that the state as received by Bob over many rounds will be something potentially entangled because Eve has used a quantum channel over T rounds, okay? So you have to use this technique of quantum definity theorems to say that if you discard a part of those rounds, then the state looks approximately like a product state. And once you have this, you have a protocol which is up to some error, essentially IID, and then you can say that the error from the ideal state that you see in the check rounds can bound the one on the estimation rounds, where you're using the quantum states to estimate the parameter. And then with this connection, you can obtain the bounds that I mentioned. They did the experiment. They saw a good accordance with ideal predictions, but they also noticed that here on the right-hand side, essentially the deviation from the ideal results that you see in practice is much smaller than the bounds. This means the bounds are very pessimistic. This is somehow expected because the bounds are very paranoid. As I said, they're taking account of any possible attack on behalf of the spy. So this is not bad news in a sense that, okay, you are effectively protected by what is going on. But of course, it also means that in a way you are being very pessimistic on the estimation procedure. In order to improve this, one probably needs to make some assumptions on the kind of attacks that are happening in the channel. I will move on to the second topic. So this is bit commitment. I don't know how many of you are familiar with this, but it's a classical cryptographic primitive that was introduced, and it's very connected with coin flipping, for example, and can be framed as a game. So the game now is that Bob has a bit that he chooses, and he wants to keep it secret from Alice until he decides to reveal it. And in the meantime, he will use this value to do some computations. And Alice, at the same time, wants to be sure that the bit he decides at time 0 is not changed. Okay? So that's a commitment. Bob chooses a secret bit that he cannot change by sending some proof to Alice. How will he ensure to Alice that he's not cheating? He will send some proof, some kind of proof system. Then the protocol needs to be hiding, in the sense that the bit value remains hidden from Alice until Bob reveals it. And then there is an opening phase where Bob reveals the value, and then it has to be binding, in the sense that Bob will reveal the value and Alice will check if he cheated or not, and she will be able to catch him. Seems something impossible. It's kind of impossible indeed. So the first important result was in 1997 by Myers. He showed that it's impossible even with quantum mechanics if you are assuming that Bob has unbounded power. Okay, so you do what you do also in classical cryptography. You put assumptions. You can put assumptions which are based on physical constraints or computational constraints. So a long line of works, at least in the quantum community, has been putting constraints like on memory or on time separation and so on, showing that with certain constraints, which are kind of motivated, it can be hiding and binding the protocol. So going back to this network setting, we decided to analyze a situation where those two Bobs, they can agree on the bit with classical communication, but they're separated, okay? And they have to make the commitment convincing Alice that can share quantum states with them. The only arrow which is not red, meaning it's classical, is the one between Bob 1 and Bob 2. So they are bounded by LOCC operations, essentially. It's easier to talk about separable operations for mathematical reasons. And you can imagine that there's some way that Alice can use entanglement to ensure their honesty, because they cannot, let's say, change the amount of entanglement, okay, what they send to them. So the commitment phase starts with Alice preparing this somewhat more complicated state of many parties. It's an entangled state. You have an ancillary system that acts as a label, if you want. And then for each value of the label, you produce a system on essentially three parties. A party which remains with Alice, and two parties that I call B here. One will go to Bob number one, and one will go to Bob number two. Okay? And these, again, if you look at these states, they need to be in the class of essentially absolutely maximal entangled states, which is kind of a guarantee that they have a lot of entanglement. Okay? For example, a G at Z. So Alice will send party B1 to Bob 1, and then Ancilla and party B2 to Bob 2. 2 makes the commitment by measuring the Ancilla. He can measure the Ancilla in two different bases, computational basis, if he commits the bit equal 1, or Fourier basis, which is mutually unbiased to this one, if he commits a bit equal 0, and he gets an outcome. He sends proof of the commitment by sending the outcome randomized with a permutation that he only knows. Okay, and then this is how the states look like depending on the commitment. If you know the permutation and the outcome, you see in one case we have maximal superposition of the other case, of the states and the other case, guarantees hiding in a sense. And then in the opening phase, Bob announces the bit and the permutation to Alice. They send back the quantum states, and Alice can check, essentially by doing a projective measurement, checking which of the states it is. So I'm not going to go into the details of the proof, because it's a bit technical, but the idea is that if bit 1 has been committed, then the state of Alice and the two Bobs is of this form. You see there is still some index that is that remains to Alice, and this part is a set of orthogonal states that are product in the partition B1, B2. Instead, if B equals 0, on the same parties, we have another basis which has maximal entanglement in the same partition. This guarantees that the two Bobs, using only separable operations, they cannot deterministically switch from Y to X. And also the fact that there is this additional superposition controlled by Alice means they cannot do this even using quantum channel, something probabilistic. On the other hand, the protocol is also hiding because Alice cannot distinguish the two states holding only this part of the system, essentially. These X are, the proof works with arbitrary dimension. The higher the dimension, the more binding it is. Scales as 1 over d, I think, or 1 over square root of d. The important thing is that you have to find a dimension for which these A and E states exist. There's a table, but usually larger than 7, I think it's fine. And also for 3, for example, you have G at Z states. And that's it. Okay, I'm leaving time for questions, I hope. I keep looking at you because you're down here and, Yanis. Okay. So essentially, try to think of a couple of simple applications of a scenario where you have a quantum computer sitting somewhere and the ability to ship quantum states to a remote place. One is sensing that allows to keep quantum precision, but also security against attackers. Fences. And the other one is a cryptographic primitive where the security is guaranteed by essentially the adversaries not being able to share a quantum connection. If you prefer, here are the links. If you prefer estimation, you can see this one, and if you prefer big commitment, you can go to the other side. And that's it. Leaving time for questions.
Oh, wow. You immediately, you were first. Yeah. Sorry. Many thanks, Matteo, yeah, for this nice talk.
Yes, thanks a lot for the nice talk. So I had questions about this bit commitment protocol. So now that I read this, can you go back to your last slide? Sorry. So I'm confused now. Is it valid under LOCC so they can share entanglement or SEP condition? Now I'm confused. Let me ask 3 questions.
I will forget about the 3 questions.
Okay, so maybe
yes. So they are bounded to do separable operations, the 2 of them, which means essentially they don't have quantum communications and they're sitting at distant locations.
But can they pre-share entanglement?
With Alice?
No, but can Bob1 and Bob2 share a maximally entangled state before the protocol?
Yes. Won't help them.
Okay. And then
because they would need to be entangled with Alice. That's the point.
So my second question was, so from what I understand, it is unconditionally secure under this assumption.
Yes.
Okay. And my last question was, can it be made device independent? So here Alice is trusting the state she's preparing, stuff like this, but can you like get rid of these assumptions?
No, we didn't think of that. But maybe yes. Not
and there is no work in that direction existing?
At the moment, no. It's a good point, of course. I don't know if people have tried with other big commitment schemes to do device independent thing. We can talk about that.
So I have questions on the 2 protocols, but to follow up on bit commitment, the permutation is known to who? I mean, how is it shared?
The permutation is announced at the end.
Okay, so
Alice won't know it, because if Alice knows the permutation, she can do some statistics.
Okay, but then maybe you need a statement that even that knowing the permutation, having done some measurements previously, you cannot decode after that. I mean, it's not only that you cannot decode without the permutation, is that you cannot decode when you don't have the permutation when you measure and after you've got the permutation.
Okay, so I think this is connected with the definition of binding that you give. This one is guaranteed under what's so-called technically weak binding. So if you want some binding, we're still working on that, because you have to generalize the protocol a little bit.
You might
and you have to tackle the permutation thing.
It's not free to have a shared permutations. Yeah. And to come back to your first work, is it so I understand that you work on a block of states. I mean, state it's like a block of channel use, like a bit like in QKD.
Yeah.
But does it implies that Bob needs to have a large quantum memory to process?
No, Bob measures immediately. Bob measures immediately in the one-way scheme, and in the two-way scheme, he encodes the phase and sends back to us.
So how can you, because you in your protocol, you somehow adapt whether you say an estimate?
Randomized. Bob tosses a coin. Each time he gets a state, he decides what to do.
Yes, but to know the estimate, you need to have statistics, right?
Yes, he will announce the measurement results after they checked. So he discloses, they do the experiment. Each time he receives quantum communication from Alice, he tosses a coin and decides one of these 3 things. And he keeps the measurement results stored in a classical memory. Then there is a phase like parameter estimation in QPD where he announces only the check.
Okay. Yeah.
Because there is no phase written there. They check, if they like it, they go ahead.
So it can happen that you can have attacks and then you realize afterwards, right?
Yeah, that's why the two-way protocol doesn't guarantee security, because you will realize only afterwards, in a sense, if it's leaked.
I just want to give a comment. So when I explain bit commitment, I like to do it classically, that you have a safe, and I like more this explanation. I think for people who haven't seen bit commitment, that's very intuitive to understand this. So